let's talk about sitting on top of the heart with the thymus, right? What type of cells do what in the thymus? T cells. They mature in the thymus. The thymus is a lot like college for the T cells. Okay, the T cells come in as sort of blank T cells, and then they sort of pick a major and get trained. It's a very harsh college. 90% of them die, or more than 90% of them die on their way through. So the ones that come out are helper T cells, or cytotoxic T cells, or other kinds of T cells that have learned that they have been tested with their randomly generated receptors. They function. They don't attack your own body, and they're able to connect to the other kinds of receptors that they need to connect to in order to be able to make your immune system work, to make the adaptive immune system function. So then, after maturing in the thymus, they go out. That's why younger people have larger thymuses, and then as people get older, the thymus gets smaller and smaller because your immune system is still in training when you're young, and then it's matured, it's developed when you get older. So you can have your thymus taken out and be okay, and the older you are when it happens, less of a big deal it is. It actually visibly shrinks over the course of your life. It starts off really big compared to really sizable organ, and then ends up like a little spot on top of the heart. Lost a lot of weight pretty shortly up. Okay, and then on to the nervous system. Okay, so in the neurons we have neuroglia. What are neuroglia in neurons? Neurons are like the brain cells and the nerve cells, and the neuroglia are. You may not be familiar with. The neuroglia are the microglia, the astrocytes, the Schwann cells, and the oligodendrocytes. Okay, so they are the support staff for the nervous system. Non-neuronal cells that you see. So here we go. We've got the neurons right here with an axon, and then here are the oligodendrocytes providing myelin sheaths on the axon. Remember, axons require myelin sheaths to be able to conduct effectively, right? And you have different cells providing myelin sheaths. When you have a lot of neurons close together, like here in the brain, you're going to have these cells called oligodendrocytes. They've depicted it here like each one makes a couple myelin sheaths, but in reality, each oligodendrocyte can service up to 50 axons surrounding it. So they make a lot of myelin sheaths. Outside of that, you don't have a bunch of neurons close to each other, so there's no need for oligodendrocytes. So instead you have Schwann cells, and Schwann cells are tiny little cells. Each cell makes up one myelin sheath. Besides that, we have the astrocytes here, which are always depicted sort of hugging a blood vessel to indicate that their role includes metabolic support of the neuron, but we shouldn't discount that they might play a role also in computation of the brain as well. They might have some sort of functioning in how the brain works as well. It's not just the neurons doing computation. But yeah, these guys keep the neurons alive, feed them and take care of them and stuff. And these cells are the microglial cells, and they have, among other functions, they have immune. They are phagocytic. They can gobble up pieces of cell debris, and if any bacteria get past the rest of the immune system into the brain, these guys' job to engulf those and phagocytose those. Right? So here are neurons and the neuroglial cells. The brain matter looks different. The nervous matter within your brain or spinal cord or whatever, it looks different based on whether it has a lot of cell bodies in it or a lot of myelinated axons. Okay? If you have a lot of myelinated axons, the myelin is a fatty material, so it's going to look white. All right. Whereas if you have a lot of cell bodies, it's going to be darker. So we talk about gray matter and white matter. Right. Gray matter is where you have the cell bodies taking place. That's where the actual cells are. White matter is just mostly axons with myelin sheath running through. So it's mostly like the cables connecting the different sections of gray matter. There's quite a lot of white matter though, because a lot of the nerves can be interconnected over long distances. Like you have to be able to send and receive signals from here down to your toes all the way, right? So there's quite a lot of axons running through your body, and then lots of the neurons in your left and right half of the brain are going to be more connected to each other, and then connected from here to the rest of the body and everything. So there's something like 100,000 miles of connections in your brain. Really huge number. Now, when we talk about these connections, when these neurons here, their axon runs off somewhere, and then you have the axon terminal. The axon terminal does not actually connect to something. It just hovers right before something. So there's a very close, it's an extremely intimate thing here, but so here's the myelin, here's an axon, and the axon ends here, okay? This is called the axon terminal, and this is whatever the next thing it's supposed to stimulate is, okay? And so there's this little gap here, which is called the synapse, okay? So it's a very, very tiny gap, so the rules of physics are a little bit different. You generally think of fluids, diffusing into something as being a slow process. But this is a tiny, like, submicroscopic distance, so that fluids go across it very, very rapidly if you open up some fluids into there. So this comes down, the signal comes down the neuron as an electric charge, as a depolarization of ions across the cell membrane of the axon. You've got these myelin sheaths, and then right between them you've got these gaps called the nodes of Ranvier, right, where the ions can be allowed across to sort of refresh the electric signal. And then you come out from the end of the axon might branch into many axon terminals to potentially stimulate many different things. So then here we have the synapse, and these materials are released into the synapse. What are those materials? When you release from the synaptic terminal, from the axon terminal, you release these substances into the synapse to stimulate whatever comes after that. Those substances are
particles.
What?
Particles?
Yeah, but what kind of particles?
Neurotransmitters.
Neurotransmitters, right. And neurotransmitters like dopamine and acetylcholine and all those different kinds of neurotransmitters. And that will stimulate or, unstimulate that cell. Cells can be unstimulated isn't a good word. They can be inhibited. Okay, so some of the connections, instead of turning them on, it'll make whatever's after that less likely to fire. Okay, so that's a single neuron can integrate signals from many different sources, and then all the go and don't go signals have to be integrated into one decision about whether that particular neuron will go or not go. Because remember, neurons cannot half fire. They can either go or not go. That means our brains are digital, not analog. Okay, kind of interesting thing. Like your ear works as an analog sound detection system in terms of the eardrum and the ossicles and everything. But when it gets to the actual nerves, and those nerves are going to be conducting the signals to your brain, nerves conduct in a digital fashion. Okay, so the brain is digital. You can actually grow a brain cell onto a computer chip and have cross communication between those two, because they do work on the same principle of electrical stimulation, and they're both digital. Okay.
Yeah, thing I don't know if it was like an MIT or something where a guy invented a robot by connecting a bunch of wires in a fashion similar to neurons.
Oh,
and somehow the robot was able to learn how to walk.
they've done amazing things like that. Like, they actually took a brain and put it in a robot body. Even that lamprey brain, they put it in a robot body and were training it to move around and everything like that. They used a lamprey brain because lampreys are so primitive that the life support requirements are minimal. They just use like cold salt water. Put the brain into like cold salt water nutrient solution and it stayed alive long enough for them to put it into a robot and have trained it a little bit. They've done all kinds of amazing things. They've even turned robots on with they've even produced self-programming robots that can feel how their body's moving. And you know how babies are born. Babies don't know how to walk around or anything like that. So they spend like months just like doing this, you know, until they can like reach milestones. Like they grab my toe and it sucked on my toe for a while, you know, and things like that. And then it takes them even longer to be able to do anything like get up and walk around, right? So they did that with a robot. They designed a robot, not programming the robot how to walk, which is a huge job. It takes people forever to do, to program a robot, because like every single thing has to be done, or else the robot's going to fall over. Like, you know, you'll put a block in front of them and they just won't know how to walk around it or whatever. So they just turn this robot on and program into it a desire to move, but no knowledge of how to do so, and just like flail your arms randomly and see what works for you and what doesn't work for you. And they made it feel good to the robot if it made itself move. And so they were like kind of stimulating it to learn. So the robot just kind of flailed its arms around for a while, and then it like figured out this really weird, awkward gait to sort of like drag itself across the floor after a while. So, you know, self-programming robots, neural networks, I think what you're talking about is a neural network, and even cybernetics where like living brains can be used to control robots and things like that. All that stuff is the work. And even biobots, where you take you build robots simply out of tissues and stuff like that. Like you can take pieces of plastic and pieces of muscle tissue and things like that and arrange them and make robots that will do things that are made out of flesh, you know, instead of steel and wires and things. So, yeah, he talks about robotics, a lot of exciting things. Okay, of course, the neurotransmitters that come out, you have to clear that away very rapidly, right? Because while those neurotransmitters are in the synapse, you have an on signal, right? So it has to basically instantly, as soon as the signal is received, that stuff has to be cleared out. And there's all kinds of problems, like diseases and poisons and things like that, that's the point of attack, right? Like, if you keep the neurotransmitters from being released, or you keep the neurotransmitters from being recognized, then you can keep that synapse from ever triggering, right? You can keep that neuron can fire all day, and the other side will never receive anything. Conversely, you can do things so that you can't clear away those neurotransmitters. Those neurotransmitters are stuck in the synapse, and then that neuron will be stuck in the on position. So you have things like neurotoxins, like sarin gas and stuff like that. Some of them work in that fashion. So, yeah, if you suffer from this disease, it will cause the neurons to, you know, be in the on form, and the on form, and you cannot clear away the neurotransmitters. They'll get stuck in the on form, and then these people end up clinched up like this, and you know, it can kill you like this. Like the contractions can be so severe, you can even like break your own back from the contractions. You cannot relax any of these muscles. And of course, they can cause asphyxiation, things like that. There's different forms of paralysis that can be caused like this. The neurons are very delicate, and they don't heal very well. They cannot go through mitosis once they differentiate into neurons. Most of them cannot go through mitosis. And the axons, of course, are very long and very, very thin, so that if they're ever severed, that's, you know, you're probably going to lose the ability to sense or control the affected organs. Parasympathetic and sympathetic divisions of the peripheral nervous system. Okay, if we're talking about things stimulate one or the other, right? Like if you are assaulted in an alleyway, like you step out from the club to get some fresh air or something like that, and someone jumps you and starts knifing you or something like that, what peripheral nervous system division can be stimulated by that experience? That would be the sympathetic nervous system. You have a very strong boosting of the sympathetic nervous system if you get a shiv in the ribs in our alley somewhere. Okay, what about if you get home from work and you sit down in an Easy Boy with a big piece of cheesecake? What kind of stimulation is that? That would be the parasympathetic division. Okay, So, gentle cuddling, eating food that you like, lying down in a comfortable position, all those sorts of things are stimulatory to the parasympathetic division, whereas the sympathetic division is fear, excitement, that kind of stuff, exhilaration. Yeah. Okay. Reflex arcs. Where are they located? Where are they actuated? In the spinal cord, right? Reflex arcs are going to be actuated in the spinal cord. Okay, so if you touch something and it burns and you jerk it back, that actual decision doesn't even reach your brain. Okay, it has to actuate in the spinal cord. That gives you the advantage of you can react faster than if it went to your brain and you said, my hand is sitting on a range that's turned on. Maybe I should pull my hand back. That way instead of doing all that, you jerk the hand back simultaneous to the conscious reception of the pain. So you're like, the same time, like your hand is coming back and you're like, oh, I've been burned. That gives you faster reflexes than what would be possible. Right? That's why reflex arcs are located in the spine. For certain things, the body has just adapted to, being able to make some decisions locally if they're very dangerous. So, all right, where in here, if we look at the parts of the brain, what's this big wad right here called? The cerebrum. Okay, a lot of gray matter in here. And then the connection between the left and right halves of the cerebrum is this right here. What's it called? Corpus callosum. And then over here you have this. What's this called? Thalamus. All right. Right beneath the thalamus, you've got this cow udder-looking thing. That's the hypothalamus, and dangling off the hypothalamus is the pituitary gland. All right, here we have the brainstem made up of the midbrain, and then what's this top bump? No, the medulla oblongata is the bottom bump. The top bump is the pons. And then this is the medulla oblongata right here. All right, so what's this thing right here?
Cerebellum.
That's the cerebellum. All right, so heartbeat and sneezing, where's that actuated? The medulla oblongata, okay? What about thinking about what you want to do tomorrow? Cerebrum. All right. What about, okay, let's get if you get damage to the cerebellum, what kind of activities would you have a very noticeable problem with?
Lack of mobility.
Yeah, walking, coordination kind of thing. So this woman right here has damage to her cerebellum, and so you can see that she's in a position that indicates that she's not entirely comfortable with. She doesn't feel stable, right? She feels like she might fall over, so she has trouble walking because the cerebellum. So she can still. It's actually a different part of the brain that says, okay, move your legs, and send signals out to your legs and stuff like that so you can walk around. So she is actually still able to walk around, but she doesn't have coordination while doing it, right? So the cerebellum doesn't do that. It just helps you do it a whole lot better, okay? By incorporating a lot of, corrective signals and really very rapidly correcting little mistakes that you make based on sense information that you get. So it's kind of complicated to say just in one thing what it does, but if you just say like, yeah, the cerebellum is necessary for coordination, that's a pretty accurate statement. That's basically true. Also, let's see here. So, which of these parts is necessary for memory as far as we've talked about? Memory and emotion, things like that. The thalamus. Yeah. Memory is actually really complicated. There's several different places in the brain where, and we still don't understand everything about how memory works. But we do see memory problems in people who have damage to the thalamus. So there are a lot of the aspects of how memories are made, a lot of that is handled. in the thalamus. Memory, emotion, and also attention and things like that are sort of controlled by that. And what are the meninges again?
3 layers on the outside of the brain.
Yes, 3 layers on the outside of the brain. Okay. Okay, excretory system, what does it do?
Control weight,
What kind of waste?
liquid and solid.
What chemicals mainly?
Nitrogenous.
Nitrogenous, yeah, nitrogenous. So what organs are in the excretory system?
Kidneys,
Kidneys, bladder, stuff
Bladder,
like that.
yeah.
Urethra and ureter are in the excretory system. All right. Let's talk about the nephrons. Okay, here we have the nephron, the functional unit of the kidney. Your kidney is made up of a whole bunch of these. Each of these things does the job of the kidney, and your kidney is just a giant wad of lots and lots and lots of these nephron things.